Hello and welcome to the AQUALIS Sustainable Water Compliance Summit session titled Breaking Down PFAS, What Lies Ahead for Municipal Drinking Water Treatment. I'm Bob Crossan, Editorial Director for the Water Group at Endeavor Business Media. To begin, let me explain how you can participate in today's event. First of all, if you have any technical difficulties during the event, please put your question in the question window and our technical experts will help you out. We recommend disabling any pop-up blocking software or extensions in your browser, as these can also cause issues with our webinar player. Additionally, we welcome your questions during today's event throughout the entire session. We will answer as many questions as we can as possible during the Q&A session at the end of the presentation, so feel free to send in your questions at any time during the session. To do so, simply type your question into the question window on the side of your screen and hit the submit button. Also, please be aware that today's event is being recorded and you'll be notified via email when the archive is available. It will be available on demand after the event. At the conclusion of the webinar, you will receive an email with a link to download your certificate, which can be used to submit for credit with Stormwater University or to serve as one professional development hour for attending today's webinar. Now, let me introduce today's speaker. We have Alan LeBlanc. He is Senior Vice President, Discipline Leader for Water Treatment at CDM Smith. He is a civil engineer with nearly 30 years of experience in water treatment design and construction. Al is inspired when, quote, when smarts and diligence translate to real world benefit, whether the project is small or large. It inspires him to see amazing results from the solid use of fundamentals and attentive engineering work. His expertise lies in municipal water and wastewater treatment, PFAS removal, hydraulic piping and pumping analysis, sanitary and storm sewer collection systems, application of sustainable design concepts, and construction cost estimating. He has also served as a chair of the New England Waterworks Association Filtration Committee for 8 years and has led training courses on filtration and granular activated carbon absorption design and operation for the past 17 years. In addition, he received the CDM Smith's President's Award for Mentorship in 2017 for his tireless work to guide and encourage young engineers. His passion project involves leading the charge to study and treat forever chemicals, aka PFAS, the entire point of today's session, and other emerging contaminants, doing cutting-edge work that's helping set the standard for the water industry, like the study and design for PFAS removal in Westfield, Massachusetts. Now, over to you, Al. Take it away.
Okay, thank you very much, Bob, and we'll get rolling. With any luck, the slide is sharing. And so yeah, we're gonna get rolling. So breaking down PFAS, what's ahead for the municipal drinking water treatment market? A hot topic, clearly, and it got hotter come March of this year, maybe 5-6 weeks ago, when US EPA announced some big things on PFAS. So we're going to talk about PFAS through the lens of a drinking water treatment supplier, and hopefully you in the audience are either those people or work with those people. Today, what we're going to talk about, we'll just kind of warm the crowd up. Most folks know about the PFAS issue in general, but we'll talk about the background, the detection of PFAS, the regulations for sure. We'll talk a good bit about treatment in the drinking water arena. Lots to think about. We'll talk about the testing, design, construction, operations steps in tackling the PFAS challenge. We will allude to what's ahead, right? What are the future treatment approaches and what are the challenges? And then we'll wrap it up with a few take-home messages. So again, as that I didn't realize we had such a lengthy introduction, but as the introduction said, this is through the lens of a drinking water treatment, platform. So let's start with the background. What are PFAS? How do we detect them? What do the regs say? And we'll get going like this. So again, if you're relatively new to this, which some are, right? Not all states have tackled PFAS until now, but the terminology is per and polyfluoroalkyl substances, right? So that's PFAS, PFAS. You have heard some people in recent years or past years refer to them as PFCs or PFOAs, but the proper terminology these days is PFAS to refer to a family of chemical compounds that is many thousands of compounds are in the PFAS world, many thousands. The two most famous PFAS are PFOA, PFAS. They both feature the impossibly strong bond between carbon and fluorine. The C to F bond is one of the strongest bonds in chemistry, and we're going to allude to that later. So these are man-made chemicals. You'll find them, in Teflon products, in the Gore-Tex jacket that you might own, in the unhappy frying pan that you see in the little image, the Teflon coating, but also, microwave popcorn, fast food wrappers, Scotch Guard on carpets, cosmetics that folks will wear, lipstick. So lots of products contain PFAS, and here we are talking about PFAS in the drinking water supply. So it's all around us. And again, just warming up the crowd, some are already aware of these things, others are not. So the PFAS vocabulary, you'll hear people talk about long chain PFAS and short chain PFAS. And so the long chain have a greater number of carbon atoms than the short chain. So PFOA, PFAS, which I showed on the prior slide, or what they call C8s. They have 8 carbons. And so PFOA, PFAS, the two most famous, they're in the long chain category. Largely, no pun intended, predominantly the long chain PFAS compounds are the ones that are regulated by various states in the country, and primarily are the focus of the US EPA's recent announcements. Long chain PFAS are easier to remove, generally speaking, than short chain PFAS. The long chain PFAS are the ones that bioaccumulate in a person's body as well. And so that makes them important. If I picture bioaccumulating these long chain PFAS in the tissue of my body, intuitively that doesn't sound good, and they can build up over the years and cause me harm. So long chain PFAS has been the target predominantly, but short chain PFAS have come into greater focus in recent time. We're going to talk about where these come from. This presentation is largely not a question of who done it, right? We're not trying to find the guilty parties. That's not the mission of this presentation. But inevitably, water suppliers will ask, or the customers will ask, where does this stuff come from? And so it could come from a whole bunch of different places, which is fairly disturbing, right? Facilities that use firefighting agents such as AFFF, aqueous film forming foams, AFFF. Facilities like airports or fire stations have used AFFF for decades, and that is a PFAS-containing product. So if we're near, say, a military installation or an airport, an industrial facility that trains to fight fires, AFFF may have been used and may be a source of PFAS contamination when released to the environment. You can picture people being trained to put out fires, foam gets sprayed everywhere, and after the training is done, it's washed down into the stormwater and into the ground. So that's a common pathway. Manufacturing air emissions is a disturbing pathway for PFAS. They can travel through the air, like the second bullet suggests. That's been the case in upstate New York, southern Vermont, southern New Hampshire, where deposition of PFAS through the air has been seen. And then there are other sources, right? So landfills are another potential source of PFAS release. It's been seen to be true. Wastewater plants, unfortunately, they're the unfortunate receivers of PFAS. Nobody should be mad at the wastewater people by any means, but it's received at the wastewater plant, as you can imagine. And inevitably, some of that can end up in the biosolids, which has been the subject of conversation in that aspect of our water wastewater industry. So PFAS is all around us, unfortunately. Back in the good old days of 2013, UCMR3 had systems of certain size, larger systems, looking for 6 PFAS compounds. And so it was a select group of utilities at that time looking for a select group of PFAS. They're also looking at a very high detection limit relative to the detection limits that are available now. So UCMR3, as I said, the good old days, was a detection limit somewhere in the range of 10 to 90 parts per trillion, whereas now we're a good fraction of that, 1 to 2 parts per trillion. So the point is, back in those days, it was somewhat a coarse characterization of who had PFAS at a high reporting level. Now, with greater vigilance and finer detection limits, we're finding it in more places. And lo and behold, the dots get more numerous as we fast forward to 2022. This is available from the Environmental Working Group, and they publish these online finders of PFAS locations. Lots of dots on the map as of 2022. There will become even more dots as UCMR5 comes into play this year. UCMR5 has people looking for 29 different PFAS compounds plus lithium. So that's 29 out of thousands of PFAS compounds. But again, a lot of people will be looking for a lot of compounds at a much lower laboratory limit. So the dots will become numerous. Again, this background, as I said, is available online through the group that I mentioned. Each dot is clickable, and you can get a little information on any given dot on the map and learn a little bit more. And so as we've evolved into this whole field of practice, the question is, boy, what do I do if I have PFAS in my water supply? What do I do? In some cases, folks have the ability to either temporarily or permanently remove a source. If I have one particularly bad well with a lot of PFAS and the others are pretty good, then maybe I can do without that well or that water supply for some time or forever. If I have the luxury, I might be able to change water supply sources. Again, it's always been a fundamental of water supply, water treatment, go after and use the best water you can use. Third bullet, blending sources to achieve PFAS compliance. In the graphic to the right on this slide, that's an image from back in the UCMR3 days, 2013, 2015. Blending was a pretty viable approach. Blending was a sanctioned, allowable approach. I did it in Massachusetts myself. And that was viable when the limits were, say, 70 parts per trillion or even 20 parts per trillion in Massachusetts. As we've gotten down to, say, 4 nanograms per liter for PFOA or PFAS, blending is much more difficult to make to be a viable solution to compliance. Then, of course, fourth bullet, treatment to remove PFAS. We'll talk about that a good deal in this talk. I've alluded to the evolution of PFAS analysis. I don't come to you as a laboratory professional per se, but there are a variety of methods out there. US EPA method 537, 537-1 came along and expanded the list of analytes. UCMR3 had their own limits, which I alluded to earlier. I should note that UCMR5, not on this slide, but UCMR5 is very convenient to the user in that they steer you toward what laboratory methods are acceptable for use under UCMR5. So again, point is that the evolution of laboratory methods has been noteworthy over the years. More in the way of evolution or progress over time, if you will. The US EPA back in 2009 had a health advisory. They said, gosh, PFOA, PFAS, they look like bad actors, and we're going to put a health advisory, 400 parts per trillion, 200 parts per trillion. And those are very big numbers compared to what we're seeing now, right? 2016 comes along, 70-70. Post 2016, various states, I'll allude to that in a second, come out with their own take on how things shall be. June of last year, some very aggressive health advisories came out. Those are shown in the lower right of this slide. These health advisories were so low that they were not measurable in the case of PFOA, PFAS. So, besides saying non-detect, you couldn't really prove that you were as low as those couple of levels, which caused a lot of angst amongst water systems, rightfully so. And last bullet, I guess it's not the regulatory environment, but it's the public push. I've embedded a couple of big screen or small screen specials on PFAS in this slide. The Devil We Know was a Netflix series. Dark Waters was a big screen production with the big people and the A-listers. Both were well done presentations of PFAS, but what they did is they certainly raised public awareness of PFAS to some degree. And I think they also caused quite a bit of concern amongst the public. In my opinion, they did an appropriate job profiling some of the folks, say in West Virginia, that had great amounts of PFOA, I believe, great amounts that cause livestock to become unhealthy and die, and other humans to have problems. It's certainly worth remembering that the concentrations of PFOA were extraordinary compared to what most water utilities see. So it can have the effect of really extra concerning the public. So that's a little commentary there. As of last year, the state regulatory environment was really something else. US EPA had their health advisories, but not a nationally enforceable standard for PFAS. And with that, you had individual states making their own evaluation of toxicology and risk tolerance. And the question was, how shall we regulate? And without reading each of these or any of these to the group, you can see that different states had a different view on toxicology, on risk, on what they considered to be appropriate. And so many states took their own action. A lot of states took no state-specific action, but it really was a wild scene and still is a wild scene in terms of state-to-state uniformity. I alluded at the top, the US EPA announced some big stuff March 14th of this year, and I'll speak about what they announced. But that information was published in the Federal Register. We are into the public comment period, which ends May 30th. The US EPA is targeting a final rule to be published later this year, early next year. And compliance would be required, if all goes to plan, 3 months after that date. Before we're done, I'll mention that figuring out PFAS and implementing a solution is possible within 3 years. There's a lot of steps to get through it, though. There's a lot of work to becoming compliant. What did EPA say on March 14th of 2023? They said, we are suggesting a draft MCL for PFOA, PFAS, both at 4 nanograms per liter, right? So it's measurable, but it's very low. And they said, we're also introducing this hazard index, which is a unitless index computed by the formula on the screen. So the concentration of, say, PFBS divided by 2,000, which is a health-based concentration value. So it's the sum of those 4 elements equals the hazard index. If the hazard index is over 1.0, you are needing to take some action. So these are pretty aggressive thresholds. Again, PFOA, PFAS, long chain PFAS, relatively easy to remove. Same for PFNA. But if we get towards something like PFBS, Gen X, those are not long chain, and they become a little more challenging to remove. So we'll keep going on there. PFOA, PFAS, there's concern that they are carcinogens, and that is certainly always a serious matter. Again, I work with toxicologists at my company. I am not one of those, but as you can quickly see, these other compounds outside of PFOA, PFAS carry their own health concerns at particular concentrations. So, again, none of these potential issues are to be ignored. They're significant concerns if they come to bear. I'm going to transition to some remarks on PFAS treatment. That's largely where I've made my living. I've worked as a water plant engineer for almost 30 years, and probably the last 7 or 8 with quite an emphasis on PFAS. And so if we're in the realm of water treatment, domestic public drinking water treatment, we are frustrated to be reminded that PFAS is not removed by traditional means, right? The carbon-fluorine bond that I mentioned, it's pretty stubborn. So if we're flocculating, settling, clarifying, filtering, chlorinating, using UV, using ozone, none of that removes PFAS. Even the more porous membranes, microfiltration, ultrafiltration, they don't remove PFAS. So it's frustrating. Even a robustly arranged water treatment system often does not remove PFAS. However, 3 primary approaches. Granular carbon adsorption is certainly a means to adsorb PFAS, particularly the long chain PFAS. Anion exchange swaps ions, as the name would imply. That's an effective removal mechanism for PFAS. And then the tighter membranes, nanofiltration, NF, and low pressure reverse osmosis, RO, those tight membranes can reject PFAS. I should add powder activated carbon is also a possible solution. Powdered carbon is practiced at plants, for years for other purposes, but it's been shown to have some benefit in the world of PFAS management. If we look at a slightly aging Water Research Foundation review of PFAS treatment effectiveness, we see that the longer chain PFAS, and I've circled a number of them in green going down the left column, a number of longer chain PFAS are quite well removed by the technologies that I've described. And this particular WRF document also confirms what I was saying earlier. Some of the other traditional water treatment processes are ineffective at removing PFAS. So again, we're zeroing in on the treatment systems that do the job. There's so much going on with removing PFAS. It might be easy to say, well, I'll put in some granular carbon and off I go. But it becomes a series of important water quality questions. At the top, it says feed water quality, right? So what water am I sending into PFAS treatment? It's not necessarily the raw water. It's what feed water. Am I taking filtered water and running it through PFAS treatment? So the questions become, what PFAS compounds am I treating for? It makes a big deal if I have a bunch of Gen X, which is not well removed by GAC, or if I don't. So, what compounds am I treating for? What's my state saying? And also now what's the US EPA saying? And, am I designing to be flexible to meet future regulations if more compounds are regulated? So a bunch of PFAS questions to ask oneself, which is probably obvious. But in the second column, what else am I doing, right? I might have a groundwater well, for example, that is going into the distribution system, maybe with just a little bit of chlorine. But now that PFAS is discovered, I start taking a closer look, and perhaps we find that there's manganese in the water supply. To the extreme, manganese would potentially hinder the removal of PFAS. So it may turn from I got to treat PFAS to a manganese removal and then PFAS removal treatment challenge. So, knowing all of the non-PFAS water quality characteristics is incredibly important. And then last column, you got to ask yourself, what could interfere with my PFAS removal? A common bad actor is natural organic matter, or total organic carbon, TOC. The TOC can compete for adsorption with PFAS. So in the case of GAC, anion exchange, my removal media may not last terribly long if I have elevated TOC. So lots to think about, best carried out by, good water practitioners. Another way of looking at it, there's so much more than PFAS. It's an incredibly complex set of decisions to make in any treatment challenge, including PFAS projects. Yes, it's a PFAS challenge perhaps that we have, but it's also, am I considering the operations of the facility appropriately? Is it appropriate to put in a lot of complex stuff, or is it better to keep it simple because we're staffed only part of the day? Always got to figure out hydraulics at a given facility. Always got to figure out permitting. So it's a myriad of considerations. It goes way beyond just how do I remove the PFAS. It's all of that goes with it. It's good water system planning and engineering that is required. A couple of quick examples in the simplest form. I might have a simple well pump, and we may be installing PFAS, obviously, somewhere in this pipeline. And I ask myself some questions about what else might be in the water, right? So that's a fairly straightforward application. Here, I might come upon a system that has a well pump and green sand filtration, let's say, for iron and manganese removal. And the question becomes, where do I put the PFAS treatment? Putting it before green sand might bury it in iron and manganese. It might blind the media. That has happened in some instances. Thankfully, not on my jobs. But, so where to place the PFAS? Probably downstream of iron and manganese removal. If I'm using anion exchange, I don't want free chlorine or permanganate going from green sand to my anion exchange. Got to think about that. And of course, is a sewer nearby. And then here I have a situation, another just example. Maybe I have air stripping for VOCs. Where do I put the PFAS? Do I have iron and manganese? In this case, putting PFAS treatment downstream of the air strippers ended up being the ticket. It seemed that removing VOCs let a downstream granular carbon process work more effectively than if we asked the granular carbon to remove PFAS and VOCs. So always lots to think about. A few words about the choice between granular carbon and anion exchange. Broadly speaking, we need lots of empty bed contact time, EBCT. And EBCT, empty bed contact time, is just a measure of how long the water is in contact with the media. And so I need a fair amount of contact time with GAC, but less contact time, appreciably less, with single-use anion exchange resin. That means I need a lot of GAC compared to less quantities of anion exchange to do the same job. The bed life is very variable. Sometimes it can be said that anion exchange resin lasts longer, but it's a very interesting economic trade-off. I've found remarkably that these capital and life cycle cost analyses are very competitive between GAC and anion exchange. And so, very interesting to see these play out. Both are reasonable and viable choices for PFAS removal, particularly in water that is low in TOC, low natural organics. I'm going to comment on a case study of some folks that have tackled PFAS already. These folks get after it in late 2016. They're using GAC adsorbers. Those are the pressure vessels shown in blue in the top image. Between the lead vessel and the lag vessel, I'll explain that in a second, we have 20 minutes of contact time. Parallel operation is approved on this job when the city runs maximum flow 4 MGD, which is a rare event. So day in and day out, they're pushing around less than 2 MGD. And they do run in lead lag, through the lead, through the lag, and out the door. This job took 30 months to execute, $5.5 million construction cost. These folks have been going over 30 months now, and they're next to an airfield, and their source water of PFAS, it was, I think, 213 parts per trillion. The great news is they've been removing those regulated PFAS in Massachusetts to non-detect for over 400 million gallons of throughput over 30 months. And they have not backwashed once, which is a really good story. So if they can do it, others can do it too. That's a lot of PFAS to remove, and they're doing well. Lead lag, again, quickly, running in series is also referred to as lead lag in PFAS world. I get a long contact time, EVCT, by going through one vessel and then the other. The lag serves as somewhat of a safety net. Parallel operation is legal in the states that I'm aware of, and that allows for greater throughput, but arguably less of a safety net downstream of the removal vessel. Quickly on a large scale, Anaheim, California has a number of sites around the city of Anaheim, and they've gone with an ion exchange solution. That was identified as the preferred technology through some really good pilot work that OCWD and their consultants carried out. They have 9 systems in design and construction, treating over 70 MGD worth of flow. So that's a huge program. The job is very much in action now, but you can see they go from water supply well to pre-treatment in the way of cartridge filters. That's a prerequisite for ion exchange systems. It's a single-use IX system, and eventually out to the distribution system. And you can see there's all kinds of interesting arrangements, really, in any case. Here we are next to a tennis court, trying to not look too obnoxious with the new equipment. So some clever screening is put in to somewhat hide the system. This is a 4,400 GPM system. This would be much larger if it was GAC, right? More contact time, more media means more vessels, bigger vessels, and probably a more obtrusive aesthetic in the end. So ion exchange was attractive from an aesthetic, how big are the vessels perspective as well. Lots of folks have discussed using treatment medias in combination. Some have said, can we use GAC as a upstream buffer for anion exchange, right? Maybe we remove some organics, or maybe we protect the expensive resin by using GAC up front. And perhaps that's an approach that allows multiple treatment objectives to be addressed, right? Maybe I'm shaving down TOC and then removing PFAS, and I'm reducing disinfection byproducts. Again, there can be consideration of multiple treatment systems in combination. It does result in more money, more unit processes to manage operationally, but it is something you see as you look around the world of PFAS in the United States. Quickly, here's a case of folks that went all the way to reverse osmosis, low pressure reverse osmosis, LPRO. These folks are treating surface water from the Cape Fear River. They had PFAS, including Gen X, which is somewhat prevalent in North Carolina and a fair bit less prevalent elsewhere. But it's Gen X, it's other PFAS, and it's other contaminants of emerging concern. So there's a lot of stuff to remove, not just some long chain PFAS. And in the end, LPRO is the right choice for these folks. 48 months, $70 million, and LPRO was the preferred choice for these folks. So at 41 MGD, that's a large case study, and it was the right solution for them. And again, it's absolutely on the table, particularly as shorter chain compounds come into focus in the world of PFAS. We're going to talk about testing, design, construction, operation. There's a lot to be said for doing a bit of testing before we go hog wild. Rapid small-scale column testing is a proven technique in the laboratory in a controlled environment to examine a given source water and how it cleans up with various treatment media. And I think this is incredibly important. We do this at my company in our laboratory, and it's an opportunity to see which commercially available product will perform best. In my view, I'm happy to send a system's water to the lab, have it run through 2, 3, 4 different products and see which one works best. It's pennies on the dollar. It's darn good insurance. I don't want anybody spending significant money constructing a treatment facility only to be disappointed at the results after it's built and started up. So again, we do this without bias. I don't care what product wins the race. I just want to know which one works best. And I think it's effort well spent. RSSCT, rapid small scale column tests, they've been used for PFAS compounds, including on anion exchange resin. This is a newer concept, RSSCT, typically for GAC, but on low TOC waters, it's been demonstrated to be applicable. And again, the benefit of this RSSCT, we get results from a controlled laboratory setting quickly. We are not waiting on a lengthy pilot scale test to play out. However, that is not a disparaging comment on pilot testing. Pilot testing can follow laboratory RSSCT work. Pilot testing certainly can catch the real world hydraulic conditions in the field, the starts, the stops, the seasonal variations. It can really shed light on how things will play out at full scale. We've seen refinement of our design concept in the field through the use of pilot testing. So good value in pilot testing, not always mandatory, but often good value. As I've stated a couple of times, the PFAS challenges we have are way more than just PFAS. I know when I'm hiring people, we don't necessarily need 500 PFAS scientists. We need people that understand infrastructure just as much as we need those PFAS scientists. So it's how often am I backwashing, and when I do, where's that waste going? It's considering the architecture involved with these jobs, right? Suddenly I have a big treatment system where I had none before, and how am I going to house that? If I'm in the southwestern U.S., it's outdoors. Northeastern U.S., it's probably indoors. And what's the building going to look like, and how am I going to get it permitted? All kinds of other practical considerations. Dehumidification for indoor pressure vessel installations. Am I leaving appropriate media delivery provisions in my civil design? And am I considering the myriad of state and local permits that are always at hand? I should say there's never relief. The regulatory people are sympathetic to those that have PFAS, but you still have to go through all the hurdles to get a project implemented. So it takes a good team to get through these things. I'm going to make mention of monitoring during operations. And so you might wonder, how do I monitor PFAS once I'm up and running? And in the picture to the right, we're looking at a pressure vessel, and that's representative of either GAC or anion exchange. But the pressure vessel has 4 circles, if you will, on the side wall. And those are sample taps to allow water samples to be drawn at different points in the media bed, right? 25%, 50%, 75% through the media bed. And operationally, we're simply cracking a ball valve, filling a collection container, and sending that water out for PFAS analysis. And we're seeing how we're doing with the PFAS migrating through the media bed. Where is the so-called mass transfer zone migrating down to? When it starts migrating toward the effluent of the vessel, it's an indication that we need to get a media change out scheduled, right? The media is exhausted, got to change it out. But to be clear, there is no online analytical equipment at this point in time. We don't have like a turbidimeter or an online pH analyzer. There's no analogous online equipment for the plant just yet, unfortunately. Also, here's a PFAS monitoring sampling plan. This was issued by a real state in the United States to a real water utility who implemented anion exchange as their treatment scheme. And they were basically required to look at PFAS, pH, and chloride coming off the anion exchange first week, third week, and then monthly thereafter. So again, fairly simple, but these are time-consuming endeavors, right? The sample has to be collected. It's going to be shipped out. These days, we're waiting 2, 3, maybe many more weeks for the outside lab to get back to us. So it takes a little bit of time. Startup considerations, there's always a ripple or a nuance everywhere. GAC, when we put GAC in service, pH coming off the GAC is typically kind of high. And it takes a little bit of throughput to return to more normal pH values. That's a common thing. There's also the lesser known fact that arsenic can be present in the GAC product. It's just a function of nature where coal comes from the earth, and sometimes it comes from the earth where there is also a bit of arsenic. And so it can take some washing of the GAC, in the forward flow direction to ride through and wash out any naturally occurring arsenic in the product. So that's probably not something the carbon industry has talked about a lot over the years, but it's certainly a word to the wise, something to look out for. Similarly, in the world of anion exchange, there's no free lunch. The anion exchange systems will typically, when they're brand new, discharge chloride to the water and remove sulfate from the water. And so the ratio, chloride to sulfate mass ratio, can be very skewed during the initial operation of an anion exchange vessel. And if it is very skewed and very different than what is historically done, it can alter the corrosion characteristics of the water. So again, I think attention is required to the water quality coming off of the anion exchange shortly after it's installed. And again, that can be overlooked. I find that anion exchange resin vendors are very knowledgeable people, but there are some instances where those individuals are not necessarily drinking water practitioners and are not necessarily in tune with that consideration. A few more comments to bring us home. PFAS media handling. If we're thinking about a carbon solution, we may ask, well, how long does the carbon last? And it's widely variable. In one case, there was a prediction of 27,000 empty bed volumes, which is a number that's difficult for most people, including me, to understand. But in that case, that translated into a 1-year life of activated carbon removing PFAS. And that was specific to one of the case studies that I mentioned. You may also wonder, how does the carbon get to my site? It's not a matter of bringing in 900-pound super sacks. It's likely, unless it's a very small facility, in the case of bulk truck delivery with eduction and moving of carbon as a slurry from the truck. So again, it's an appreciable operation, but carbon suppliers have this down to a science, and it goes smoothly in just about all cases. Another hugely important question, what is the fate of the spent media? In the case of GAC, it could be sent to a landfill when it's exhausted and can't absorb PFAS anymore. It's got to go to a proper landfill. It could be incinerated, where people thermally destroy PFAS at an appropriate temperature. And in the case of carbon, it can be reused again once it's been reactivated. So that's a few comments on where carbon goes. With the resin, it's similar with a little bit of a difference. So it could be landfilled properly. It could be incinerated to destroy the PFAS. But if we take an incineration approach with anion exchange resin, single use, it cannot be reused. It's destroyed and unusable after that incineration occurs. So a lot of interest in what will become of my spent media. Some folks, I'll just say it, they don't want to be owning that PFAS laden media forever, right? So landfill disposal is unattractive to some who are concerned with being associated with that material forever. So lots of considerations there. I'm not advocating one versus the other. They all come with cost implications. A word about the future as we steer toward the end. The first bullet in the left, media separation, GAC, anion exchange, or so-called novel adsorbents, which are kind of like the first two. Media separation is proven, and it's being practiced successfully, as I've said in this presentation. Liquid to liquid separation, membrane processes are also doing good. NF, RO, nanofiltration, reverse osmosis. There is some work with foam fractionation beginning, but as we go down the line here, concentrating and destroying PFAS, that is hopefully the future of our industry, where we can actually deal with the PFAS entirely at the treatment facility. That would be fantastic. if I can concentrate the PFAS into a very high concentration solution and then destroy it on site, so-called zap it with electricity, that would be fantastic. And it would get us out of the mode of owning spent media and shipping it off site. These approaches are not ready for prime time at water treatment facilities of any appreciable scale yet. However, there's great research in the industry by R&D or entrepreneurs or engineering companies like mine. There are a lot of folks researching these things. There's a lot of promise, say at Superfund sites where concentrations are higher or where throughput is lower than many MGD. I would suggest that we in the industry pay close attention to the concentration and destruction techniques that are being developed, support them, and be ready to embrace them. I'm hoping they are ready for prime time before my career is over. So I think it's the future, and hopefully we can all support that. Just a quick look as we're really wrapping up. What are other people doing? Is the United States doing something super unusual with their March 14th announcement at US EPA? You can see in Europe there are some similar trends, maybe even more rigorous in some cases. The sum of all PFAS be less than 500 parts per trillion. That could be a tall order as we learn to detect more and more PFAS. Denmark is showing something similar, a little more strict than the U.S. And we can see some other examples on this slide. In the bottom, we can see that PPQ, heaven help us, PPQ is being used parts per quadrillion as a measurement threshold in Europe. So, science is getting finer and finer, and we will see what the future brings. Take-home messages. This will be my last slide. So, number one, hopefully we've made the point that it is an emerging issue. Regulations are still emerging. The US EPA's March 14th stuff is a draft. Public comments are coming in. And so, that's not cast in stone yet. And then, of course, treatment practices are still evolving. So this is a very active area of water practice, to say the least. Number two, I've tried to make the point that, good holistic thinking is required in attacking a PFAS challenge in water supply. There's a whole bunch of infrastructure to consider. There's the water quality and pre-treatment needs and the avoidance of unintended consequences. For instance, I don't want to put in GAC, celebrate that I've cured the PFAS problem, and have the newspapers reporting that I released a bunch of arsenic off the GAC prematurely, right? That would be terrible. So that's take home number two. Take home number three, there are some established treatment technologies out there, GAC, anion exchange, RO. I demonstrated GAC can remove over 200 parts per trillion to non-detect for a good duration, as can anion exchange. RO is removing all kinds of compounds in one of the case studies that I mentioned. So there are some arrows in the quiver to tackle these challenges. And with that, I think I'm going to send it back to our moderator. It looks like we're on time and probably able to field questions.
Yeah, and we already have a couple coming through. We'll start with this one, which I think is probably on the mind of a lot of utilities that are out there, which is our utilities just getting into consideration of PFAS, as our state had not regulated PFAS at all until the announcement on March 14th from the US EPA. Where do we start, and what are the steps to address PFAS? So you've kind of gone over quite a lot of that, but is there like a stepping stone or a chart, or a table of actions that people are trying to use to figure out their next step?
Yeah, that's a super common question, particularly if the question comes from a state that wasn't previously regulating PFAS. So if it's one of those states, for instance, there may have been minimal attention paid to PFAS until now, and it's a case of, gosh, what do we do? We think we might have PFAS. What do we do? And I think to me it starts with good data collection effort, right? What do we have in the water with regard to PFAS and non-PFAS water quality parameters? Getting a handle on that, whether it's in the source water or the filtered water, finished water, that's number one. Number two, there's a lot to be said for a desktop study, just to take a breath and say, all right, I got some PFAS and I get these water quality considerations. What does PFAS removal look like at my facility? You know, am I into post-filter GAC? And if so, how big is it? And do I have the land for it? And what might it cost? I think those are a couple of modest, reasonable first steps. I'd also add doing some planning on your public education and public communications is probably wise too. You know, having some idea how you will communicate with the public is probably a good idea before you miscommunicate or don't communicate. So those are a few thoughts to those just starting to consider PFAS.
Oh yeah, I very much second you on the communications thing. I think that communication, we're entering into an era where you can't really be silent as a utility any longer, and you have to get out in front of these messages so that you become the expert on them. There's a lot of, we've covered communications a lot on all of our publications, and the more I get into it, the more I realize how important it is in this era of very nuanced regulations and whatnot. So we had two questions here. They're kind of related to each other and more in the realm of disposal and destruction side of things. There was one which was, where's the backwash going? Asking that as you were going through a couple of your slides. And then when you change the media, where does the media go? So, you know, this question of, all right, cool. So you've removed this product. What's next? What happens after that?
Yeah. Well, second question first. I think, where does the media go? Typical answer is proper landfill or to a proper incineration facility. That's where the media goes. We hit on that in one of the later slides. Where is backwash waste going? It's a good question. Some of the good news is that in a post-filter application or an application where the PFAS media is lightly loaded, there will be minimal backwashing of the media, right? So there'll be minimal backwashing of a GAC contactor, anion exchange contactors. Typically, you do not backwash them. But in the cases where there is backwash, typically the preferred destination is the sewer system. In other cases, a permitted discharge to another source is considered. A question we get on backwash waste, they say, well, if you're going to backwash that GAC contactor, is the spent filter backwash water non-detect PFAS? And the answer is no, it's not non-detect PFAS. There will be some amount of non-zero PFAS in the spent filter backwash. Most wastewater agencies will accept that at this point in time. I know of one who indicated concern, but that's basically where it goes at this point in time. Site-specific considerations dictate, of course.
Yeah, excellent. This is an interesting question, kind of in line with this too, which was like, is there any guidance on the regulatory classification of landfill that will accept spent media? Are there any issues with finding landfills to accept PFAS containing material?
Right. I do not have the regulatory classification designation at my fingertips. However, there are landfills in the United States that will accept carbon and resin. I know that some of the resin providers have industry partners that are more specialized in special waste disposals, right? So I don't think you'll find that the resin people are directly swinging deals with the landfills, but they do partner with disposal professionals, and there are landfills in the U.S. that will take this at this point in time.
Yeah, makes me think. So within Endeavor, we actually have an entire publication dedicated to the solid waste industry and landfills. It makes me want to go and talk to them about, hey, what are you hearing about this issue, and bring that back to the folks here in the water sector so that they understand what the challenges are from that side too. We had two more questions here that are, again, related to each other, kind of more on the cost side of things. So one was, on average, what is the cost of the new system to remove PFAS? Then the other was, how much does a single water sample cost for PFAS?
Yep. Well, I'll do the second one first again. The single water sample, I grab a sample of water. I want to know how much PFAS is in it. I send it to a lab that does PFAS. That sample could cost, say, $300 to analyze. So this is not a small thing for a water utility to start taking on the cost of $300 analytical costs per sample. So again, I am incredibly sympathetic to the water systems in the U.S. on that. Labs are becoming very busy as well. That wasn't the question, but they're getting very busy. And on average, what's the cost for new systems to remove PFAS? I gave a 4 MGD case study, $5.5 million. That was 3-4 years ago when that construction bid came in. I know of a 2 MGD anion exchange installation that was a little over $3 million 3 years ago. I know of a 2 MGD GAC job that was $5 million 2 years ago. Those are smaller case studies. I know of a 12 MGD plant that costs, I think, $35 million for a new GAC facility within a building with intermediate pumping. It's incredibly variable depending on whether I need a new pumping step to be associated with the PFAS treatment, or if I need a building, say in the Northeast, or I can put it out in the sunshine under a canopy in the Southwest. I don't like to be dodgy on the question, but it's incredibly variable depending on the site or the configuration of the facility or the geography.
Yeah. The last comment that I saw in here, and I have a couple questions of my own to fill out some of the time here too, but one was just excellent presentation. They really appreciated the basic overview and the considerations. They found that very helpful and useful. So one of my questions I had on this too was you're talking about an ion exchange and granular activated carbon. The question that I'm starting to hear from folks too is like, what does the supply chain look like to fulfill this for every utility in the country, presumably, because all of them are going to have to deal with this. Is there anything that you can share on that side of things? I know that might be outside of the realm of the treatment question, but what are you hearing when you're speaking with some of the manufacturers and the utilities on how they're addressing that?
Yeah, thus far, the vendor community is putting on a brave face, maybe a sales-focused face, and they're saying that they have prepared themselves for the demand on media and treatment vessels and the associated equipment. I think a healthy skeptic would wonder whether that ample supply is going to last. Be it carbon or resin or other equipment. I think a lot of folks are concerned enough where they're considering pre-purchase of equipment if they see themselves going down the road of treatment. And I think that's got a lot of merit in this day and age. We're very aware of supply chain issues with the COVID era. And now we have this rush on the market, perhaps with these PFAS regulations. So it's super reasonable to be skeptical of the adequacy of supply and make some alternative plans as best I can answer it.
Yeah, well, it's a really interesting question. I'm sure we're going to be talking about it a lot over the coming months and years, to be honest. The last thing I wanted to leave with everyone before we close out too is that the water group at Endeavor Business Media includes a couple of different publications, including Water World and Wastewater Digest, in addition to Stormwater Solutions. And we have covered extensively on Water World this new PFAS MCL announcement for the drinking water side of things, what that means and some of the industry response there. Our May-June issue will have a couple features on that in there. And then on the wastewater side, we're focused more on the biosolids and the challenges that are happening there. And we have a feature in the May-June issue for Wastewater Digest as well. So if you're looking for more information on PFAS, you can find it in all different verticals from us at Endeavor Business Media. But with that, that's all the time that we have today for all the questions that we didn't get to, which I think we got to all of them. If you have any other questions, please reach out to us. We'd love to get you in touch with Al to talk those over a little bit more offline. And just a reminder that at the conclusion of this webinar, you will receive an email with a link to download your certificate to use for Stormwater University credit, or 1 professional development hour for attending the webinar. That concludes our presentation. I'd like to thank Al once more for participating in today's event, and of course to all of you for joining. Don't miss our final session of the event with a keynote speaker, Darren Olian and Aaron Zaski from AQUALIS. You can join the keynote by exiting out of this event, going back into the agenda, selecting the session by clicking View Session button, and then the information for the final keynote will be available to you. So we'll see you at the final keynote.